Hey guys, welcome back to chapter 13. We have talked up until this point about reaction quotient Q. We're now going to make a little bit of a turn and start talking about equilibrium constant K. And equilibrium constant K is pretty much what we're going to talk about the rest of this chapter. So let's get started. So equilibrium constant K is a measure of how far a reaction proceeds, okay? So when we're given a value, we're given a number for K, we can tell a little bit more about that reaction. It tells us what that reaction looks like, okay, at equilibrium. For the equilibrium constant K, it's going to be calculated the same way that we calculated the reaction quotient Q. It's going to be the same formula. So it's going to be concentration of products over concentration of reactants. And then the coefficients are still going to be those exponents on there. This formula has a fancy name, and the fancy name for this formula is law of mass action. Okay, not something you're going to be tested on, but if you see those words somewhere, you know that it's talking about this formula here. Okay, so let's get to know K a little bit better. So the value of the equilibrium constant is independent of the starting amounts of reactants and products. And this is actually something we're going to prove to ourselves in the lab when we do the equilibrium lab. So it doesn't matter if we start with 0 products, all reactants. When it finds equilibrium, K will be the same value. We could start with all products and no reactants, and once it finds equilibrium, it'll be the same value. We could start with 50-50, 40-70, 40-60, whatever it may be, and it'll always find that same equilibrium constant K, that ratio at equilibrium. The value of the equilibrium constant is dependent on the temperature of the system. So if we heat up a system or cool it down, that is going to change that equilibrium constant K. And again, this is something we'll explore in more detail at the end of the semester. The magnitude of the equilibrium constant indicates the extent of reaction. So after we calculate K, towards the end of this lecture, we will look at what does K of a 100 mean? What does K of 0.1 mean? But the magnitude or the size of equilibrium constant K will tell us a little bit more about the reaction. And then I've said this before, but I can say it again. K and also Q are unitless values. So one of the things that you'll notice in this chapter is we're going to have some sort of experimental data. If we want to calculate K, or we're given K, we want to calculate something else, experimental data is a must. So we're going to be given data during this chapter. The next set of data that we're going to look at also is going to give us an indication of the first statement I made, that it's independent of the starting amounts. So we're just going to look at a series of data that somebody collected. We're going to look at the equilibrium constants and see that even though they started at different places, it all still came out to the same value. So let me talk you through this table here. So here's the chemical reaction that we're looking at. Hydrogen reacts with iodine to create hydroiodic acid. Here's where our initial concentrations. So in the first trial, they started with 0.5 molar hydrogen, 0.5 molar iodine, none of the product. In the second trial, they started with no reactants, 0.5 molar of the product. Third trial, they were all the same, and then see how we just keep mixing them up. Okay. So we mixed these different amounts at each trial. Then we allowed these, we allowed it to get to equilibrium, right? We allowed it to kind of settle into equilibrium. Then we took a measure of the values at equilibrium. Okay. So notice that starting with different amounts, so initial concentration, we have reactants, no products. Here's where equilibrium was. We have no reactants, all products. Here's equilibrium. Now, I did not say that the values at equilibrium would be the same. We see that in all of these trials, the values are very, very different. But there's something magical about taking the ratio of these values at equilibrium. What we'll find is when I plug these values into that law of mass action equation, that all of the values come out to the same. Okay? So independent of what we started with, we get the values at equilibrium, we plug it into that ratio equation, and they come out the same for a given reaction. So we'll get to prove this to ourselves in the lab as well. So how did they calculate these values at equilibrium? How did they get this equation? Let's just do a really quick example. This is going to look and feel very similar to what we did with the reaction quotient. So our reaction is up here. So NO reacts with Br to produce NOBr. What is the value of K if the equilibrium concentrations are as follows? 0.31 NO, 0.24 Br, 0.47 NOBr. So to calculate, let me get my pen here. Calculate the equilibrium constant K. We're going to take the concentration of products over the concentration of reactants. So our product is NOBr. And we're going to square that because there's a coefficient of 2. Divided by the concentration of our reactants, which is NO. That is also squared because of this coefficient. And times the concentration of the other reactant. So that's our formula. So now let's plug in the values they gave us. So the concentration at equilibrium. So right now it's kind of silly. You're like, yeah, why wouldn't they tell me this? Or why would they tell me this? But it's going to be important as we get more complex. So this statement right here tells us that we are at equilibrium, right? So we can just plug it into this equation. We don't have to do any extra work. As problems get more complex, having a statement like this and being able to recognize it is going to be really important. So at equilibrium, our concentration for NOBr, so 0.47, and that's going to be squared, divided by NO, which is 0.31, that's going to be squared, and Br is 0.24. So we plug these into our calculator, so 0.47 squared is 0.221, and then 0.31 squared times 0.24. At the bottom we've got 0.0231. So divide those two numbers, 0.221 divided by 0.0231. And we get 9.5, we'll call it 7. So what is the value of the equilibrium constant K if the equilibrium concentrations are as follows? So our answer is K equals 9.57. Pretty straightforward, that's easy peasy. Now, what in the world does that mean? Equilibrium constant is 9.57. Great. What does that tell me about the reaction? So glad you asked. So the significance, what does it mean? For a number where Kc is significantly greater than 1 or greater than 1, what that means is that the products is going to be a greater concentration than their reactants. So in order to get a value greater than 1, the number on top has to be bigger than the number on the bottom. So think 4/2, right? So both of these are going to lead to numbers that are greater than 1, and the number on top is bigger than the number on the bottom. When that is the case, we know that the forward reaction is favored. So if the concentration of products is bigger than the concentration of the reactants, that means that this reaction is going to push towards the product side. That's going to be kind of the favored side, or that's where we're going to see most of our concentration. So forward reaction is favored. Doesn't necessarily mean it's a fast reaction. It just means once equilibrium is established, we'll have more products than reactants. All right, so the opposite scenario, if we get a Kc value that's less than 1, what we know if the value is less than 1 is that we would have more reactants than we would products, right? So to get a number that's less than 1, think 1 over 10, that's a decimal. Think 2 over 4, that's also a decimal. So both of these numbers are less than 1. So to get a number less than 1, the number on the bottom is bigger, the number on the top is smaller. So that tells me my concentration of reactants at equilibrium is a larger concentration. So we would say that reverse reaction is favored, right? So we're going to lie more towards the reactants. Not very many of them are going to make products, right? So if we start with just reactants, a little bit will push to products, but for the most part, it's going to stay as a reactant. So we talked about greater than 1. We talked about less than 1. There is one more scenario that exists, and that is if Kc equals 1, right? Right on the middle. This is rare. It can happen technically, but is it going to happen? Probably not. But if it does happen, and Kc comes to a value of 1 exactly, the concentration of the products equals the concentration of the reactants, and neither is favored. Equilibrium would fall right on the middle line. Okay. So let's take a look at one more example and then apply what we just learned about what K means. So at equilibrium, a solution contains 0.234 molar cobalt, 0.355 chloride, and 0.124 cobalt chloride. What is the value for the equilibrium constant K? So calculate K. And then is reactants or products favored? So go ahead and pause the video, give yourself a chance to try to work this out, and then I will work it out with you. All right, to calculate equilibrium constant K, we're going to take concentration of our products divided by concentration of our reactants So plug these values in and I get 1.24 molar on the top. I get 0.234 molar on the bottom, 0.355 squared. So plug this into our calculator, turn it on, 1.24 divided by 0.234 times 0.355 squared. And I get a value of 42.0. So that was me calculating that K value. Now we have to determine what does that mean. Is reactants favored or the products favored? So in this case, is K bigger than 1 or less than 1? Yeah, it's bigger than 1. So what does bigger than 1 tell us? Bigger than 1 tells us we have more products than reactants. So the forward reaction is favored. So if I were to answer this, equilibrium constant K is my number, and this is products favored. All right, so that is kind of our introduction to equilibrium constant K. In the next videos, we're going to spend some time getting to know K even better, and then we'll jump into kind of the second half of the chapter. Hope you guys found this helpful.